Hi everyone, we'll start in a couple of minutes. So now we are ready to start. I hope you can hear and see me well. And today we'll talk about quite important topic in deep learning and in processing of sequential data on how can we do self-supervised learning in this scenario. During this lecture, I mostly give a general introduction on what is self-supervised learning and what kind of approaches are expected in this area and what people are doing in general. And closer to the end of the lecture, we will see on how it works for sequential data, what kind of polarities, what work, what doesn't work, and so on, if you're talking again about a specific topic of our course. So in general, I expect that we will start with definition, what is self-supervised learning, and why do we need it. Also, during this lecture, we will not focus on all parts on self-supervised learning. Rather, we will see what's going on with similarity learning, or so-called contrastive learning, which basically is the same name for two or different names for the same thing. Later, we consider, like in the second part, of what types of self-supervised learning exists, and we will see like general two types, generative and self, or no, sorry, contrastive learning. And both of them are pretty important and pretty interesting to see what kind of ideas lead to prosperity in terms of training of self-supervised representations. Then we'll consider modern similarity learning and modern contrastive learning. I will also talk about how can we deal with metric or similarity learning in supervised setting and what kind of approaches are on top there, especially related to classification with open set classification when we observe new classes, when we can observe a new class at each new object we see in the test sample and how can we deal with it. Also, we will later consider, in particular, sequential data models connected to self-supervised and to similarity learning. And we will end with challenges in self-supervised / similarity learning. That would be the end of the lecture today. Today we will also focus on similarity or contrastive learning. And next time we'll focus on approaches which I want to call after regression-based approaches. We will cover them briefly today, but mostly we will put some time and effort in them next time. So if you're more interested there, you should also visit the next lecture. So let's start with the actual content and start with a very general idea of self-supervised learning and in general similarity learning. Basically, when we are talking about distances and so on, it's very like old idea in machine learning, and we can say, okay, we have kernel methods and support vector machines and Gaussian process regressions that basically are using some definition of similarity, but in deep learning, we have slightly different motivation and slightly different like general construction on why do we need contrastive learning and in more general self-supervised learning. So let's consider some classic problem in machine learning. We have an object we have some features related to this object and some target we want to predict for an object. For example, we have a human and we are a major bank. And our goal is to predict if this user will churn in 3 months or not, if he will pay his credit or not, and so on. And so we want to base our decision on some reasonable features. And what we are doing, basically, we say, okay, let's collect some useful set of features: salary, age, education, I don't know, or whatever you can collect with an expert. So you have like hundreds of features that are somehow related to this user. And what we are doing, we at this step are constructing a representation of an object by hand, manually. So we have this representation now, and we can apply to these useful features some clever approach to predict this target. For example, we can use gradient boosted model to predict from salary and age the target variable. So we have this representation by default provided by expert and by our own expertise. And we have a classifier that is constructed on the base on data on pairs of input variable, output variable. And this is what typically works and works quite good in classic machine learning. As this is unfortunately work not so good if we consider more structured data. A typical example of structured data is an image or a text or a sequence of events. And in all these cases, the problem is that we don't have this mapping, direct mapping from an image or another structured object to an object representation. For sure, we can try to engineer some features. For example, we can use TF-IDF features for texts, for images. We can have the shift features and so on. But it is not optimal solution. These representations suffer from many problems. For example, if you consider TF-IDF, there are just too many features, and also not meaningful distances between objects at all. We have like almost equal distances for all pairs of objects, which make this distance useless. No interesting results at all if you consider metric learning and distance learning. Okay, so we, in addition to step of construction of a classifier that predicts something from a representation, we have a second problem. We have a second model or submodel related to mapping of an object to a representation of the subject. So we now have a second part of our machine learning problem or deep learning problem that is related to mapping from an image to a representation. So we can, from a representation, predict something. And typically, as we have only one end-to-end approach in the world of machine learning models, a complex enough approach, a neural network. So we will use it to train both classifier or other prediction model and the representation. Okay, this was our small goal, but we have also our more general goal that we want universal representations. We want our representation model to construct features that can be useful in many different scenarios, starting from classification of what is on this image: cat, not cat, dog, cat breed, so on. And we continue with other problems that are also quite important to some particular applications. For example, semantic segmentation. We want to select the part of an image related to a cat, or we want to estimate depth on how far away from a camera this particular pixel of an image. And in both cases, it's kind of important to look at something different. But I think that overall, these representations should be correlated most of the features can be the same. So maybe we can try to use these universal representations, or like if we are talking about something more general, about like ultimate goal is to have universal representations, to have representations that reflects all useful informations we have about this image, that cover most of the problems we can encounter into, and drop everything we don't need. So at the first place, we have these good features. At the second place, these features don't include something we don't need. Also, so from this idea, naturally, after this idea, naturally comes another idea on that if we want some universal representations that solve a lot of problems, we should not focus on a particular problem. And okay, there is some challenges connected that if we want to associate loss function connected to, sorry, okay. With each of problem, it's hard to combine them all in one simple loss function. So just waiting does not work all the time. But also we kind of tailor it to our goal and say that maybe we should use this unlabeled data we have all the time, data related to a particular type of data, for example, to all images or to all medical images or texts. And so if we use enough sample size, diverse enough, interesting enough, then we can try to construct this, our dream, our universal representation model. And also we have some other scenarios, some other motivation to consider this type of learning. We can start far away from computers and say that babies and animal learns like this. They also get most of the information from the outer world by looking at unsupervised data, like a constant series of images the nature put on you, texts we see every moment, and all this, like I think like most of the information like this is unsupervised information we observe here. Yes, there are some specific types of learning that related to like supervision, to some level data. This is good, this is bad if you teach baby how to behave. But in general, most of the concepts are perceived as ideas from self-supervised. You come to them on your own or transfer your previous knowledge to build on some new knowledge you recently acquired. Also, okay, if we are going from this heavens and this more general I don't know, neurology related learning, we can say that in business, we have other motivations to consider this unlabeled learning. At first, good supervision is not cheap. If we want good quality of labeling, we should invest a lot of time and efforts to be able to deal with it. Just because, okay, typically, a typical scenario like Toloka, Yandex Toloka, or Amazon Mechanical Turk is that it hires a lot of people. Those people are not highly qualified and they get not a lot of money for their job. And so they make a lot of errors. And it is the case not even with these random strangers at Toloka or Turk, it would be okay. But also if you're looking at like specific teams, specifically hired to make supervised data from unsupervised, there's a lot of problems again because they're not very highly qualified. They're not very motivated because okay, there is a top step as this career direction is to be like a manager of people who elaborate data. not a very inspiring perspective, in my opinion at least. And also you don't get a lot of money for this. So basically this labyrinth is again something you will not get very high quality. It's kind of interesting to see that even if we have more people assigned to the same task, to the same image, the quality does not increase greatly, unfortunately. And also, if you imagine like some large data set, like Imagenet with millions of figures, and each figure belongs to like 1,000 to 10,000 classes, you can imagine on how many efforts you should put to elaborate and how much money you put there. But you can, like an alternative, you can just parse internet and have a lot of data related to particular problem, to particular data type, images, or text. Again, then like just here you can take them and use them. You don't need to label them. And also each day we observe new data. And I think that we don't want to label this new data each new writing day. So instead we just say, let's have this data as it is and learn some representations. Also, like last but not the least, is that maybe we can like specify that we want these universal representations to solve a lot of different problems. And we hope that with these representations, we can do efficient transfer learning. We don't need a lot of labeled examples to solve another new problem. We just collect a small data set, collect no data set at all, a labeled data set, and try to solve this kind of problem here, a new problem, and solve it well. So actually, there's a lot of reasons to think about self-supervised learning, and many of them are related to similarity learning, and you will see shortly why. Okay, so let's try to split all approaches in self-supervised learning to two main types. I would like to call them generative and contrastive. Generative type of self-supervised learning is something like after regression, for example. So we say, okay, we have some example here. And what we can do, we can say, okay, this part is an input. This guy is an output. And we want to construct a model that predicts output on the base on input. If we like train a good model, and this model has some specific architecture, then we have some representations in the middle. And this representation is what we need for the self-supervised representation learning. We have another type of self-supervised representation learning called contrastive learning. The main idea here is that if you have similar objects, the representations should be similar. If you have distinct objects, then the representation should be distinct. So basically, if you have like this two balls, white balls in a Abelian space, and one black one, we have wanted this distance between white balls to be small and between white and black to be large enough. So we want after learning to have something like this in the embedding space. And so this is basic idea of contrastive learning. And they like stay on shoulder on the idea that we somehow can generate pairs of similar and pairs of distinct objects. And we will dive deeper into this part a bit later again. So we can say that if we want to solve this problem, we can represent it in this way architecture. And it's also another useful perspective to look at self-supervised learning as somehow a game between generator and not that complex discriminator actually. Very simple. For the first part, for generative learning, we can say we have this X as input. We put it to encoder, have some representation Z in the middle, decode this representation to have X hat or some new parts of X recovered. And as we know actual X, we can compare it to X hat and have this reconstruction loss that depend on X and X hat here. This is for generative self-supervised learning. If you consider contrastive self-supervised learning, we have like two objects, same encoder, two representation of X and of Y, ZX and ZY correspondingly, and we have some contrastive loss. It also can be very simple loss, like just L2 norm between ZX and ZY. But typically in modern applications, we often see a lot of approaches that focus on like more interesting losses related to this. It can be even simple neural network, and we will see today what kind of network it can be. And in this case, we have this simple discriminator, but it's not that complex, simple discriminator that says how similar are two objects. And on the basis of this, we have our whole architecture on how self-supervised learning works here. And so we have these two types of self-supervised learning. And I will focus very briefly on the first part of it after regression, about generative model. And then we will go to another part on contrastive learning. It's actually quite similar to similarity learning. If you have like this supervised setting, you can say, okay, this object should be close and this object should be far away from each other. We again fall into actually pretty similar problem related to mathematics of it, related to how we define should we define the loss and how should we train the model, but more of it later. Now let's focus on generative models. Say that we parts, okay, we have some image or sequence, and for them, we want to recover some missing part. Basically, in the very beginning, we don't have this missing part, but we can get the whole object and drop some part of it, some information. In this case, we have this missing information, and we try to recover what's missed. We can select what we missed. For example, we can say, let's drop future and try to predict future from the past. We can also try to cover some part of an image. As in this case, we parse like random crop, random part of like an image, and we randomly drop some part of it. And in this case, we have again some information to recover. We can basically try to have random patterns. Keep it here in the data, random patterns removed. And all of this work, but particular type of after regression will work in a particular scenario. Let's so like the general scheme is like this. So we have again something like encoder and decoder, and from X with some parts missing, we have something that we want to predict to, and basically we do it with this combination of after encoder. But you can think that actually after encoder has too narrow sense in modern machine learning. What you think wider when you consider this kind of construction. For example, you can say basically most of the modern language models that can try to generate new text or fill the gaps in the text are also kind of after encoders, but like slightly more sophisticated with very strange thing as representation, but trained based on the similar principles. We can say that if we have this large data set of sequences, large data set of texts, and we want to train some language model, we can apply the same heuristic. We can drop some part of the initial sequence and force the model to recover this gap. So we have this a lot of sequences, a lot of sentences from the internet. We have this start token, actual sequence. Then we have like this separator or the end token. And we also add some mask. We drop this word or a token. and try to recover it using our language model. Want to make our best guess on what is this place. Our best like try to guess is you, they, or your. And as we know the actual true value, for example, you, and we can compare the loss function between true value and something we recovered. And so we have this loss function. We don't need supervision because we just dropped some tokens in sentences we already have. And we train these models quite successfully. And like most of the modern models in language are somehow based on this idea. They also transfer quite well. And also different models have different application area actually. If we drop some word in the end, we have more after regression floor. In our model, we want to like to predict future here. If we drop something in the middle, we have more consistent representation that focuses on all the sequence equally well and maybe better suited for problems like classification. But again, let's not deep too much into the details for it, and we'll consider something like this later. Also note that we will have can combine, okay, if we imagine contrastive and a generative approach, and we somehow actually can combine this idea of after regression and contrastive encoding. And more on this, you will know during the seminar, because there you will be looking at this contrastive predictive coding model that you, okay, that's quite interesting example of what we can do with it. Also, I think it's time to mark how many of you are here. So please turn on your cameras and I will take a screenshot on who is there. Okay, thank you, Elizaveta. Thank you, Nikita. Okay, thank you, Polina. Ilya, Alina. Okay, thank you. 1 minute, please. I will like save it and send it. Okay, thank you a lot. And now we can continue with our lecture. You can keep cameras on, it's okay. And so we defined some very general ideas on generative and contrastive types of self-supervised learning. Also, there are sometimes we didn't consider a lot generative contrastive. The idea for it is that we try to put more efforts into the discrimination, and in this case, we can somehow come up with some more interesting models. So we can say that instead of very simple discriminator here, we can make it harder, make it adversarial, and so on. And in this case, we will have generative contrastive learning. Also, we didn't consider a lot some detailed approaches. Some of them we consider during the next lecture, some during this lecture, but not all of them for sure, because I think you understand that there is a lot of approaches, and you imagine the waterfall of papers each year. So you'll focus on main ideas and main papers that are either most interesting, most important to the general understanding on how self-supervised should work, or related to some sort of results, maybe not that interesting, but interesting on how to do the best, how to publish papers that says that I beat all other approaches to the moment. Okay, as I said before, today we'll focus on contrastive learning and what's the general idea of contrastive learning. So we have like this encoder F And from each image, we can create a representation. And so we do it, for example, for 3 objects: anchor, positive object, and negative object. Positive is supposed to be close to anchor, so representation for it should be close to the representation of anchor. For negative, it's kind of from different class. It's a dog, not a cat, in this simple example. So it should be far away from it. So if we have this embeddings of anchor, embedding of negative object, and embedding of positive object, we want this distance between anchor and a positive small, or similarity should be large. And for a pair of anchor and negative object, it should be large actually, because of different objects. And so after learning, we should observe something like this. And okay, how can we do this similarity learning? So this metric learning, distance learning. In the case we have some supervision, I will mostly focus on the problem on face recognition, but basically you can imagine similar problems. So in face recognition, you have a large sample, and the sample consists of a series of images. And for each series, we have, each series is an image of one person. For example, all images are images of Barack Obama, and we have another cluster of images related to Macron. And so we have collected such data sample, and we can apply this simple metric learning idea. And basically, we just don't even need some additional supervision. We have this already good supervised data, like split it to class, but we have a lot of classes. So direct classification approaches don't work here. We can train classifier with a billion of logits in the end. Instead, we try to build something that will provide good embeddings or representations. In this case, if a new object comes, we can, like a new image, we construct a representation of this new image and, and find the closest image to this new image here. And say that if we have the closest distance, that's definitely Barack Obama, or if it's closer to Macron, it's Macron, and so on. In this case, when a new class appears in the test sample, we just form a separate cluster of images related to this new class and embeddings related to this new class, and we can proceed as we had before. So we have, like, for example, again, new classes here. And if we like have a new input image, we just have embedding and look how this embedding is close to other parts. So basically, it's how we use this model in most cases. But let's discuss on how we train these models, how we can obtain like good representation. And the very basic idea, and it's not that bad actually, is a triplet loss. In this case, we can say that we have positive object, anchor, and negative object. So we have anchor and positive object here, some distance between them, and another distance between negative object and an anchor, and some margin in like that we will need. And basically, we say that if you have a pair of positive object at an anchor, we have some hard, semi-hard and easy negatives. If this negative is like here, and then we have this large loss. Basically, it is like smaller than this guy. So it is larger than m here if we have a negative object here. we have larger than m loss. If it's here, we have something between 0 and m. And here we have 0, we have easy negative here. So basic idea, if we remove the margin, we just penalize pairs of objects such that like we have negative object close to positive object. With margin, we penalize even if it's like fall into this boundary area, and don't penalize what we have outside. And also we have this 0, so after some moment we don't care actually about how far away are two objects, because we are interested more in local parts, in local similarity or dissimilarity of the objects. Okay, is it clear what the triplet loss is? If yes, please put plus sign in the chat. Okay. You understand this margin? Yes, everything else. Okay, so let's go on. Oh, okay. Okay, so basically the idea is this. Yes, there is a lot of things to discuss on the way. Maybe the important thing that you don't think a lot when you first think about triplet loss is that we somehow should get these triplets when you actually want to have some training. You just need to mine triplets from a batch we have right now. So suppose we have some batch here, and so we have up to be in the third power triplets, or at least like this is the order of magnitude of number of triplets. But let's consider like realistic scenario for face recognition that B, a batch consists of P different persons, and for each person we have K distinct images. Okay, typical value that's used in practice is 4. So basically we have B that it's P times K. And basic approach is to select all valid triplets and average the loss on the hard and semi-hard triplets. It's interesting that you should not count the triplets with 0 loss, because if you have 0 loss, then if you average it, we have overall very small loss at later stages, and this will slow down our training. So basically, we just look at hard and semi-hard triplets to work with. Okay, so how many triplets we have here? So we can select anchor in PK ways. Then we select positive image, K-1. Then we can select like negative image from all other classes. So we have P-1 classes and K images for each class. So in total, we have something like P squared, K cubed number of triplets here. And in many cases, it's too large. Also, we consider too many triplets that basically easy triplets, and so we waste our resource on them. It's a problem. So typically, people are doing a different thing, not batch all we can get for this particular batch, but rather focus on hard examples. So for each anchor, we select the hardest, so we selected some anchor image, select the hardest positive, something with the biggest distance between positive and anchor, so this guy is as big as possible. Then we find the hardest negative object that's like the closest object to our image, and we add this triplet, this 3 objects, to our training at this particular batch. In this case, for each person, we consider an image, so we consider all images. But if you select an image, then we automatically identify the hardest positive and the hardest negative object, put them, and so you form a triplet. So number of triplets equals to the number of the objects in our batch. And we're pretty selective about what kind of objects we're interested in. And so we select the hardest object in the batch. According to the research, to the papers, this kind of batches are pretty good, and it's better than all, more effective. We don't look at examples we don't care about. But basically, sometimes you should watch carefully, and we will talk a bit later about it. That as all other heuristic approaches, sometimes they don't work, and particular performance depends on a problem we consider. Sometimes the strategy would be hard. Okay, the basic idea is that if we have almost perfect model, but we have some outliers in our data sets, so some anchors and positive pairs actually shouldn't be that close because this positive object is something blurry or something completely irrelevant because of labyrinth issues, then we will have hard time selecting hard positive and hard negative examples here because we will focus on outliers, and this is definitely not a good thing to do when you are doing some deep machine learning. And you can also have degree of freedom. It's kind of triplet loss or contrastive loss we can consider. We consider it very simple contrastive loss, slightly more advanced triplet loss, but this is not the end, and there is a lot of other losses related to this type of behavior. Okay, and I will not go into details for each of them. I will try to make some general overview of the problems of them and how we can deal with them. The two main issues with this contrastive learning overall, so this fundamental, I would like to say, flaws, is expansion. It's because for each triplet we look only at 3 objects, and we can't ensure that we put all other classes from this particular class. We put only one out here, and it can be not enough. We can say, okay, we have this blue objects, we have this yellow objects here, and we start with pulling this blue object from yellow objects. So we move it this direction. But in this batch, we definitely don't consider all the classes. So maybe there is another class here, red one. We can't ensure that we are not doing some harm to our model by moving blue cycles from yellow triangles, because we are kind of don't imagine on how embedding space looks like. And so in this case, we would have this traveling point clouds in the embedding space, and maybe we can never reach this equilibrium state. Also, we can imagine, okay, we can try, okay, it's kind of simple issue, maybe, and we can try to deal with it. For example, we can say, let's have one positive pair here, but a lot of negative pairs in each batch. So in this case, we can try to pull away from all classes we have in the objects, and we sort of contrast these guys into a more dense cloud. And in this case, we have a chance to survive and to make models that does not have this expansion issue. Somehow it works, but there is a scalability issue, another one, because we need to look at a lot of data, and we can't look at all the data because, okay, the batch size is limited, and overall like number of classes is very high, and we can try to train them all at the moment and during the overall training, but typically it requires investment a lot of additional resources and does not end up in a good model overall. Also, it's like a technical advice. Typically, when you are thinking about contrastive learning, you should have very large batch sizes, because if you have small batch size, you will have issues like this, and you will end up with models that maybe is not the best model you expect. Other issue related to contrastive learning is sampling issue. You have this degree of freedom. You can consider this as an opportunity on how we sample triplets. But from other point of view, it's not an opportunity. It's another step we should take. And as we discussed before, this step depends on a particular problem we look at. For different problems, we will have different optimal sampling schemes. It's not what we want from deep learning. If we don't want to invent new optimizer and new sampling scheme, each time we see a new problem without proper intuition on how to do it, and we don't have proper intuition generally. So maybe it's not also like a red flag for contrastive learning. We can try to do it and to survive along it, but it's not always easy to handle if you have some new problem. So we can try another approach and can try to develop intuition on how can we approach this problem in a different way. Okay. Okay, one moment, please. Okay, we can try to have another approach, another algorithm, and try like a separate center for each cluster. We say that we have this ZI representations produced by our encoder. So our encoder f of x produces some embedding z here. And we have embedding related to each class. So we say that this is a true class label, and we want it to be close. If you're talking about scalar product, also we have some bias term related to each term. And if we do this in like a softmax loss fashion, we divide the score for that's actually the distance between the object to the center of a particular class, divide by the sum over all the classes we have. This embedding is related to all other classes here. We can try to do it, but as we can see below, you can observe the training dynamics for MNIST. Even for MNIST, it's not that contrastive. You have very high, like very low distances between objects related, like this embedding space, related to those images. So maybe we should try to do something more contrastive on the way. And actually, a simple regularization helps. So we have this initial softmax loss related to that we want our embeddings to be close to cluster centers. But also we have some distances between an object and cluster center, and we want it to be small. We want this distance between cluster center of the true class and embedding of the subject to be close to each other and penalize if they are not. In this case, we see a very different training dynamics. We see that these objects like kind of cluster, if we consider like missed images from 0 to 9, each image like live in a separate cluster here. And it's a good thing, in my opinion. More contrastive, even from NIST and for other datasets too. And you can clearly see it from TSNE. Also, you can see that it's like not very stable thing. because yeah, like simple affine transformations, for example, rotation will also give us the solution with the same loss, but okay, we don't care much about this here because we're happy that we are improving. But this is now not the not the final stage of the evolution of these approaches, because we still have some issues. They're still not contrastive enough, and we expect that we can do better. And one idea is to, okay, we have the softmax, modified softmax. So we basically try to move away classes from each other. But basically, if we look at angles, if we project object into the sphere, then we can do better. So basically, we have the norm of the embedding and the angle between zi and corresponding vector of the class. So this is basically the cosine distance between like zi center of the class divided by the norm of zi and I. For simplicity, we don't have biases here. So our loss has this form. We again divide some distance, in this case, like cosine distance multiplied by the norm and exponentiated between an object and the true class of this object, and divided by this term plus terms related to all other possible classes we have in our sample. So we now look at angles, and in this case, we have a better separation between classes than we had before with this intersection here, which we don't want. And this algorithm is called sphere phase. Works pretty well, but we have even better approach. Yeah, with the name arc phase. We skipped cos phase, but I think it's for good. It's not much different from arc phase. In this case, we say that now that I all has norm 1. So we don't have it in the loss now, but we have two additional hyperparameters, scaling and merging. Scaling allows us to scale more efficient if we are talking about like temperature of softmax, I would like to say. And this will help to balance on how big our margins should be, how big angles should be. And also we have this additional margin term to have some margin between two different classes, which is important. Note that this term should be selected carefully, and there is a lot of things that they actually affect the performance of the arc phase, and you should select them carefully. Typically, we can say that we should have enough, small enough values of margin and of scaling to fit like all objects on the sphere, because basically we have a sphere, and if you have too large scaling and too small margin, then we'll definitely have intersection because we will not have enough space to distinct two different classes. Some heuristics you can find in the paper, but basic idea is that you should pay attention to it. But the second idea, that's good news. Arc phase, at least like from what I know, is the best approach we have. It's slightly better than cos phase, but it's definitely better than softmax and sphere phase. This is because we take a right look, a right angle when looking at the problem and consider better embedding space related to that we want all objects to belong to some sphere of the unit radius, and we should use cosine distance instead of linear distance to make them look better. Maybe in your problem some other distance would be better, who knows? But in general, in images, it's like this. Also, let's look at some example applications of this type of losses and how they work, how they for particular challenges. The first challenge we consider is quite recent, 2019, and we have a lot of images of whales, and we want to identify a whale by its tail here. And you can see that's kind of challenging problem because all 9 images are from the same whale. And so also it's kind of imbalance problem because for some whales we have bigger number of images, for some smaller, and we have a lot of fuzzy challenges in the way. And there is a lot of engineering tricks involved in producing the best solution, as it's quite common for Kaggle. But basically, if we are looking at algorithms, we can say that both arc phase and triplet loss are important for producing good solutions. Also, focal loss we did not consider because of time limitations and lack of focus. It's also have somehow to deal with it. Also, when we consider cost phase, also can be a part of the winning solution as well. 9th place, not that good, not that bad. Also, when we consider alternatives, we can say that if you have Siamese network, we can just put this Siamese network that say if it is the same or different images, same will or not. It's like solution number 4. And the first place in this competition actually did not use this contrastive learning, similarity learning approaches. They have some classification models stacked together to rule them all. So in some cases, it also can be useful to train, for example, models that train everything like this with some clever and smart engineering on top. So be it. Another challenge related to large number of classes when we need similarity learning because we have new classes in the end. And we have typical problems for this kind of challenge here. The first problem is class imbalance. For Eiffel Tower, you have a lot of images. But for example, we have some boathouse in Seattle, and we don't have a lot of photos related to it. So it's kind of typical. So we have for some classes thousands of images, for some only 10 or less per class. And also, as in other real-world conditions, as most of the test images actually from new landmarks, from objects we did not observe in training. So it's also a challenge, but it's like a challenge that happens in the real world. Also, there is Labyrinth Issues. The data is noisy. It's collected like by crowdsourcing, and typically we have not very good quality. Also, we have very large variability of inside classes. For example, you can imagine that we have some photo of Eiffel Tower from the outside for some bridge in Paris, and we have some images taken inside the tower or on top of tower. And in this case, it's going to have a very large diversity for classes. And so what work and what doesn't work here. Okay, it was 1 year later. So arc phase, cost phase, they used in all solutions in the top star. And like the era of triplet loss ended there because triplet loss were popular, but not the most popular choice. Again, first place takes some clever look at the problem and came out with some classification related solution. Third place uses some variants of subcenter and dynamic merging, enabling another update of arc phases. Also note they don't use a lot of preprocessing and all this kind so stuff. So basically, it's sometimes you don't need Kaggle magic to win or to have good solution. You can just rely on modern papers to have a good result. So basically, we can say that right now, argfakes dominates and related approaches dominates the similarity or deep metric learning in most cases, but also it's not always the case. I emphasize that sometimes in unsupervised setting, which we'll consider a bit later, we will force to use another approaches, and that typically works a kind of better. Also, you should put a lot of attention if you have this auto distribution examples in your training or test set, because in this case, this approaches like argface or triplet loss can pay too much attention to these outliers that we don't want them to do like this. So now we consider a different types of works that is focused on contrastive learning for self-supervised. So again, we want this anchor and positive objects to be close and anchor and negative object to be far away from each other after learning. But right now we have no supervision, we have self-supervised problem statement. And in this case, we should generate these pairs, these triplets online. And this is what we can do actually. We have an image and we can produce two views of the same image. We have an image of a cat. So we crop and resize back to the original size, the image. And we have these new images and we consider them similar, okay, because of they represent the same object and we definitely know it. Also, as negative image, you can have like any other image in the data set, the same. So we want to put together these two views of image and push apart different views of different image. Okay. And basically it works with some kind of triplet loss. But it's interesting that top solutions try to do on top of this by considering a more complex architecture. So basic architecture is like this. We have some image. We produce two views of it by some augmentation, random cropping, random color distortions, random Gaussian blur. Then we have this encoder to produce representations here that we want. And this would be truly unsupervised or self-supervised representation here that can be used to solve any problems. And also it's typical to consider projection heads, like additional simple network that produces from representation some projection into simpler space. Somehow it turns out that it works better. So we maximize agreement to disagreement in this projection of an initial space. If we want to have some inference, we say that we throw away this projection head and we use only encoder. And so we have this representation to solve some downstream task to train a logistic regression on top of this problem. And what we see from the paper, why do we need projection head? So it's really the case that we need it. And the answer is yes. Let's consider three scenarios. The scenario when we don't have projection head and train some models, train some representations, and to use them as it is to solve some downstream problem. As far as I can remember, it's top one Imagenet, but I can be mistaken. And we have two types of projection heads, linear and nonlinear projection head. And we Change the size of dimension of Z of projection head here and compare all these three approaches. And what we can see, the top one accuracy for non-linear projection head is the best. It has some significant gap between linear and non-linear approach, with non-linear being better. So non-linear projection heads are better than linear projection heads. And also we have some serious boost of the performance when we compare a projection head to no projection head when we use embeddings at the last layer as what we want. Quite interesting observation, but okay, it's how the practice works. We can say that the reason why do we need this projection head is when we use this projection, it loses some important information, but it is for good. It allows you to compare what's important, what's not important. And this intermediate before the projection presentation are somehow better because they don't drop a lot of useful information. Because basically what we're doing with this contrastive learning approach for self-supervised, we generate some views, and this view, like as you can see, of different types, some random cropping, color distortion, Gaussian blur. So from one point of view, it's limited number of distortions of how we generate the news. From other point, we don't cover all we want, maybe. So basically, we can try to say what's for some simple problems, how different embeddings work. So we have this column for initial embedding and this column for representation of this embedding. And we solve like color versus grayscale, rotation problem, original versus corrupted image, original versus Sobel filter. And you can see that in all cases, this representation is more useful when you say about the accuracy of the solution of this particular problem, with like the gap being significant in all four cases. And when you compare like this random guess, this projection is like quite closer to random guess. And this ash before the projection head, our embedding f of x, is much better than projection head and random guess, so we definitely need it. And we have some explanation why do we need this projection heads. Okay, so this was the approach like in 2020, and it requires actually some negative mining. It requires this approach to sampling of negative objects. Can we avoid it? Can we try to train only using positive pairs? Because if we generate some views, we are sure that this will keep the semantics. If we have like some negative mining, then maybe we have some negatives that actually is a positive just because of random. And it can be crucial at later stages when we focus on batching the most difficult cases. And Bayol provides a framework to think only about positive pairs. Okay, we consider two networks, so-called online network and so-called target network. Online network is something we train, we learn it here. And target is a rolling mean exponential moving average of online network. So we have this like training, we have over the epochs, and online is what we want to learn right now. And target is some average of, like we have this epoch loss, and so we have as the target some exponential moving average of previous steps. So there are two nets we learn only online, but everything else in the framework is quite similar. We have some input image. We want to generate a pair of positive images. So we generate two views, V and V prime. We construct representation with online network here, and here we use target network. Then we have this projection head, again, kind of different from for online and for target network. And also we have this another projection here, additional projection to make it work. And so we compare this projection of the encoder, online network encoder, and projection from the target network. And we compare them, and we want them to be close to each other, and somehow it works. We have very good self-supervised learning. We don't need any labyrinth. We just need to have this views, a good generation, good augmentations here. And if we do this, we say that we obtain quite good representations. For example, let's consider how we measure the quality of this type of approaches. Okay, if we are still in the image domain, we can try to use Imagenet for evaluation. So we use Imagenet for self-supervised learning, for supervised learning, and for strong supervised learning. So supervised learning with some additional tricks. Okay, we have some augmentations and so on. And so in the end of the training, we have some representations. Then on these representations, we train a logistic regression, basically a linear classifier on top of it, and see what's the quality of this classifier training using obtained representations. If these representations are good, then the quality of the final model should be good. If not, then not that good. So basically, we test if this even linear projections of obtained representations can provide good quality for as complex problem as Imagenet. And it's really the case. When we use Biol or Biol X2 or Biol X4, then we have quality quite close to supervised baseline, and the gap is especially small if we have large number of parameters. My hypothesis is that as we learn something self-supervised, we need more data, more features, more parameters to have the model of similar quality. But it's interesting that we are quite close to supervised baseline here. And even for 25 million of parameters, the gap is not that large. It's like only 2%. And also you can note here that we have this SimCLR approach here. Okay, gap is larger. And we also have this CPC approach. It's even worse here, but okay. So this is how we can test it in one way. We can test definitely in different ways our Biol architecture. We can use a lot of problems to test the quality of transfer learning in two ways. The first way is just to have some linear features on top. The second way is fine-tune these features. Not only these features, but carefully tune all the network. Then we can see that typically Biol wins. It wins compared to supervised approaches and to SimCLR approaches here. And okay, it means that this supervised approaches, is quite good and comparable to what we have in supervised. Another type of problems, another type of testing we can do for Biol and other self-supervised approaches is to consider a completely different problem. We consider semantic segmentation and object detection. And also we consider depth estimation when we want to estimate how far away an object from the camera. And we can see that in this case, we have even better solutions than self-supervised approaches in all the cases. Maybe these problems were somehow carefully selected to demonstrate the performance of Biol, but nevertheless, it means that, okay, we have kind of amazing increase in metrics when we consider the self-supervised approaches, when we consider it's better than MOCOS and SimCLR and so on. So if we drop this requirement to drop negative pairs and construct this clever procedure, we can do even better. And kind of amazing, kind of another magic in deep learning. I think you saw a lot this 2 years, but it's another sign that we are dealing with a miracle. But when we also can try to decompose on why this miracle happens, because we have this ablation study section in each paper. And the first thing is that we need large batch sizes. We compare the quality of the solution compared to the considered batch size. Again, we consider top 1 accuracy for linear evaluation on Imagenet. We have also some specifications, but we don't care much about it. We can see that if we use SimCLR, that the accuracy drops in a very fast way, just because we use both negative and positive pairs, maybe. So we need larger number of these positive and negative pairs to work. For Biol, this decrease is not that significant, but if we have like only 128 examples, that definitely will have some drop, significant drop of performance. So we need large batches to train good self-supervised models. Also, it's crucial to select augmentations on how we generate these views. If we use only crop, we have not very good performance actually. We drop for SimCLR is crucial, minus 25%. Biol quality drop is also significant, minus like 13% here. If we add blur to generate views, we have slightly better quality. If we have this remove color augmentation, okay. If we have this grayscale augmentation here, so we are doing grayscale here, we have better quality. And also we have that C for SimCLR, the most important, in addition to crop augmentation is to this color. Sorry, is this gray? It's not color here, it's not grayscale, it's color here. Is grayscaling of the images for some reason. Maybe it's because this it's very important to keep the information about colors when we are talking about SimCLR. It's also important for Biol, and this increase in performance is also quite important. So we see that all approaches requires large batch sizes, and correct augmentations are crucial to get the good quality of the model here. Okay, this was the SOTA for 2020, but it's already 2021. So there is a new SOTA for self-supervised learning based on kind of sample principles. But again, with both negative and positive pairs. The idea here is to measure the correlations between embeddings produced by images, and this embedding should correlate highly if we have two views of similar image, and different when we look at correlations, at feature dimension for different feature dimensions. So we have this like more structured representation, and we say that we keep all information on the diagonal and we don't have high correlation between features. Maybe this also can be good for disentanglement, but okay, I didn't look into it. If we do like this, so we have two terms here in the loss function. The first term related to that we want correlations on the diagonal for features of the embeddings to be close to 1. And also we have penalty for the values of the diagonal. So it should be as close to 0 as possible. Okay, for correlation, we have this usual formula, don't care much about it. And we can say that we can beat Bayol typically when we're using this Baron twins approach. Okay, it's not the case, for example, for Imagenet here. If we use top 1 or top 5 accuracies for Imagenet, we see Bayol slightly better than Baron twins. Also, we have another approach we don't talk too much about it because we have limited time, and actually we are kind of close to the end of our lecture. But sometimes for some problems, we can do significant improvement. For example, when we consider semi-supervised learning, somehow for semi-supervised learning, Barrow twins starts to win. So in this case, we have like 100% of images presented during this self-supervised learning stage. Then we use only top 1 or 1% to 10% of random images with labels to fine-tune these models. And we can see that right now we have better quality for Barlow twins than for Bayol. So we can say that somehow it's better for semi-supervised learning. So kind of interesting idea. And also we have other comparisons, but I think we can end right now our lecture. And okay, stop at this point when we are saying that right now we have a lot of interesting approaches, a lot of heuristics, and the performance is amazing. Actually, we can train like good Imagenet recognition models using this self-supervised approach. And it's again kind of amazing that we don't need negative pairs in self-supervised scenario. Also, during the lecture, I like that we covered also another part of the literature related to supervised contrastive or similarity learning. And you can also see that there is some additional work connected mostly to face recognition in this area. So I think that's the end of the lecture for today. Thank you for your attention. Good luck with the seminar and overall with your routine today and during the weekend. And so be it. Goodbye.